In this video we're going to look at the continuity of piecewise functions, and our job is going to be to state the intervals of continuity, but there are a few things that we have to do before we do that. First, we need to look, step 1 says determine the intervals of continuity for the individual functions. So ignoring the fact that we're only using the first function for values that are less than or equal to 4 and the second function for greater than 4, we just look at the function itself. X squared minus 5 would be continuous everywhere because it's a polynomial. And the function f of x equals 4x plus 11, that would also be continuous everywhere since it's a polynomial function. What's happening is in a piecewise function I have two separate functions that are being used on different intervals, and what I really care about is what's going on at x equals 4, because that's the only point left. So what I have to do is look at the limit as x approaches 4 from the left and the limit as x approaches 4 from the right. And I also want to look at f of 4. Remember, my goal is to find out if a function is continuous at a point, the limit has to exist, and that limit has to equal the function value. So the limit as x approaches 4 from the left, I would be using the x squared minus 5 function. So that would be 4 squared minus 5. 16 minus 5 is 11. The limit as x approaches 4 from the right, I'm going to be using 4x plus 11, because this function is being used for x is greater than 4. So I would take 4 times 4 plus 11, which is equal to 27. And f of 4 is going to be the 4 squared minus the 15, because that's where the equal sign is. So that equals 11. Now I really didn't even have to find f of 4, because I already know, because these two are not equal, that I do not have continuity at x equals 4. If the limit doesn't exist, then I don't have continuity. So the interval of continuity would be basically all real numbers except for 4. So I show that using interval notation. So the intervals of continuity are negative infinity to 4, union 4 to infinity. Alright, let's look at the next scenario here, and we'll look at the individual functions again. They're both polynomials. So if they were just standalone functions, they would be continuous everywhere. There's no point of discontinuity on those individual functions. So both functions would be continuous everywhere if they were just standalone functions, and so our concern is what's happening at 3. So we want to find the limit as x approaches 3 from the left, from the right, and we want to find f of 3. The limit as x approaches 3 from the left, we would be using the x squared minus 6 function, because that value is good for the intervals that are less than or equal to 3. So we'd have 3 squared minus 6, which equals 3. Then the limit as x approaches 3 from the right, we're going to be using the 2x minus 3. So that would be 2 times 3 minus 3. So 6 minus 3 is 3. And f of 3 is actually the same as the limit as x approaches 3 from the left. That's 3 squared minus 6, because the equal sign, that's also equal to 3. So this function, not only are the individual functions continuous on their own, but when you graph them together, when you graph the pieces of them together, you still get the same value at x equals 3. So this function is continuous everywhere. There is no point of discontinuity. The interval of continuity is from negative infinity to infinity. What I'd like to do now is show you how to graph a piecewise function on your calculator so that you can see the difference between these two functions. I mean, you can graph them by hand also, but it's nice to be able to do it using technology. And so the first thing you do is you type, so in y1, we'll type in the x squared minus 5 in parentheses. So x squared minus 5, close the parentheses, and then I'm going to multiply that by the x minus x is less than or equal to 4. So we have to have closed parentheses, and we'll hit X. Now to get the less than or equal to, we go into second math, which is test. So second math, you see we've got the equal signs and less than or equal to signs, and we're going to arrow down, or we can hit just the number 6 and that will give us the less than or equal to. Hit 6. So I want x is less than or equal to 4. I close the parentheses, and now I add the second function and its interval. So open parentheses, 4x plus 11, close them, and we're going to multiply by the x is greater than 4. So x, we go to second math or test. This time we want greater than, so we're going to hit 3, and that's going to be 4. X is greater than 4. Now I'm going to start by just doing a zoom 6, and I know already that this isn't going to show me the whole graph, but just we can play around with this. So that's just giving me the parabola, but remember a zoom 6 just gives you a 10 by 10 window, and I already know that one of the functions is x, that the value of f of 4 would be 11, and in the other function when I plug 4 in I'd get 27. So I need some larger values here on my y-axis. So I'm going to go into my window, and I'm going to leave the x values alone, but my y min, I'm going to leave that at -10. I'm going to arrow down and make my y max, let's say 40. All right. Might change the scale to around 5 just to make it look a little neater, and then I'm going to graph it. All right, and so it's not pretty, but you can see what's happening here is that the limit as x approaches 4 from the left is 11. So as x approaches 4, my y value is 11, and if I trace, let's trace on 4 so you can see that. Right, my y value is 11. Okay, if I jump to, in order to jump up to the other function, I can arrow up. I should actually, sorry, probably have to arrow to the right. Arrow to the right, and you see I'm on the other function. If I trace 4 again and hit enter, you'll see, oh, it jumped me back down there. The reason why if I trace 4, it's always going to jump me back to this original function is because that's where the equal sign is. But either way, you can see here that there is a big gap in the function at x equals 4. And we can also, if you arrow to the right, you can jump to the next function and see that at 4.25 we're at 28. If I arrow to the left, I can see I'm approaching 27, but we know that at that part the x equals 4 is part of the bottom function, not the top. So at this point what I'd like you to do is I'd like you to pause the video and see if you can graph this next piecewise function on the calculator using that same method. It's basically just your first set of parentheses is the function, and then the second set of parentheses is the inequality, and you set it up as if it were a multiplication problem. You use the plus sign between them, and remember the buttons to help you find the inequalities are second function and math, or second test. So try that.